website for interested researchers for listening to your talk, and maybe they want to get onto something that they like and they want to revisit so that they can look into that talk and listen to that talk again. So I just seek your permission once more.
Yes, yeah, no problem at all.
Perfect. KK, can you start recording also then? Yeah.
Started.
Okay. Perfect. Uh, so welcome everyone. This is another seminar in the ICWaR Seminar Series, and like every time, we have a very distinguished guest with us, Dr. Vinayak Shidekar. He's an
It
assistant
started.
professor.
Yeah.
Excuse me. Sorry. Can you all please, all the audience, I request you to kindly mute yourself. So the way it goes is that we have only Professor Vinayak as the speaker. So he's only unmuted. We all listen to him, and at the end of the talk, we'll anyways invite anyone to interact with him. Yeah. So kindly mute yourself. Yeah. Okay. So yeah. So I was saying that we have a distinguished guest with us, Dr. Vinayak Shidekar. He's an assistant professor of agricultural water management in Department of Food, Agriculture and Biological Engineering at the Ohio State University. There are so many things that he has done, and I think he currently also holds several positions, such as he's the executive director of the International Program for Water Management, and then the overall Danish Education and Research Program. Again, he's also running one of the longest running training programs on agriculture training, Danish, I think, design and installation. He leads the AG Water team, which works at the intersection of agriculture, water management, water quality, and soil health to promote sustainable and resilient farming systems. So I guess this is very much relevant for Indian ecosystem also. I mean, given the kind of changes we are looking at, either due to climate or humans, I think we have to be mindful of what we are doing to the system. So his research is very much relevant for us, and I think very much interesting for everyone working in the center. So I invite Professor Vinayak to kindly take the stage and yeah, give his talk. The talk will be around 30-40 minutes, completely up to you how you want to do it. And then once you're done, you let us know, and then we'll open the floor for interaction. Thank you very much.
Thank you, uh, Professor Vishwakarma, and thanks everyone for joining. It's only just after midnight here in the US, so uh, hopefully I'll try to keep my energy up throughout my presentation. But I'm really glad to be here at this forum, and I never imagined that I'll get an invitation from IISc to present my work. So I'm really excited about that. We do get a lot of bright students from IISc here at OSU or in the US, and it's always a pleasure to be working with someone who has been trained at your institution. So I think the topic we decided to talk about today was kind of looking at the modeling of hydrology for subsurface drained watersheds. I'm hoping that I can give you enough of a overview in the amount of time that I have on this topic area. I'm making some assumptions in terms of how much you know about these systems. So, but I wanted to start my presentation by just giving some regional context for where I am and where I work. So this is the state of Ohio in the US, and if you put a dot right in the middle of the state, that's where my university is, Ohio State University. And I also wanted to kind of start my presentation by acknowledging that we still maintain our roots, even if we have lived in the US for 17, 18 years. My family and I were very much connected with India, and this is my daughter Sanvi, and my wife Asmita works at OSU. She's also a faculty. She actually did her PhD from IIT Roorkee before she joined here. So we have the privilege to work as colleagues in the same department, which is kind of a unique situation. As Brahma mentioned, I do have multiple hats that I wear. We'll skip that for now. We can come back to it. I do want to acknowledge the team that I work with. A lot of the work that we do is dependent on all of these outstanding students, technicians, and postdocs that we have in the team. Um, as Brahma mentioned, I kind of my program is a mix of multiple topic areas. I always struggle to figure out what exactly to use as a theme. So I usually divide my work up into three topic areas: hydrology and water quality, agricultural water management, and then soil health. Are the three kind of main topic areas that I work on. What we're going to talk about today is only one of those aspects as it relates to hydrology and water quality. So within that bucket of hydrology and water quality, I do a lot of field scale monitoring of these parameters, as well as we do a lot of field scale and watershed scale modeling of these. And then more importantly, for improving water quality, we do a lot of evaluation of the conservation practices. A lot of our focus is on agriculture and water as it moves in the agricultural landscapes. Um, we do have another faculty who primarily focuses on urban hydrology and water quality. So a lot of my work is involves working with farmers, conducting on-farm research, but then more importantly, keeping the profitability and sustainability in mind for those agroecosystems that we work on. Soil health is something I kind of got involved because of my interdisciplinary background when I was doing my master's. A lot of what I do relates to agricultural drainage, and I wanted to put things in perspective for all of you. For especially agricultural drainage is not something that everybody learns in their academic curriculum. I'm an agricultural engineer by training, and we at least go through some of that education. But if you look at the the global scale, out of the entire cropland, about 14% of that cropland is assumed to be to have received some kind of artificial drainage. And but if you look at the need for drainage across the world, about 40% of world's cropland actually can benefit from drainage. So there is a tremendous potential for agricultural drainage to expand. Irrigation was probably the first water management practice that expanded across the world. However, drainage has kind of fallen behind because of the initial capital cost that is involved. It's very expensive to install drainage, not easy to install drainage. United States, majority of our drainage exists in the US Midwest region. I'll have a map on the next slide. But we estimate about 40%, 37% of our cropland is drained. And the state where I live in, Ohio, about 30% of our cropland is assumed to be drained, 3 to 4 million acres, or somewhere around 1.5 million hectares out of the 7 million acres that we have as a cropland. Sorry, out of the 13 or 14 million acres that we have, about half of that cropland is we think that it will benefit from drainage. So still there is a lot of potential for drainage to grow, but I always say this about the Midwest region. It's one of the world's most intensively drained region, and Ohio is somewhere here. And if you look at the northwest corner of state of Ohio, that is definitely one of the world's most intensively drained areas. What you see here, the darker color means the percentage area of a county, which is equivalent to a district that has received artificial drainage for crop production. So we do have some counties in Ohio that have 80% to 90% of the total county acreage that has received artificial drainage. So it's very prominent. And the reason we here in the Midwest region, we need drainage is first, on annual basis, we get almost the same amount of rainfall as India here in Ohio. By the time you get to the other parts of the Midwest region, it's a little bit less, but on annual basis, we get about 100 centimeters of rainfall. Half of that rainfall comes during non-growing season and very cold season, November to April. A lot of times the temperatures are closer to 0 degrees Celsius, so almost no evaporation. But we get half of that rain during that non-growing season. The other thing we have here in the Midwest region is poorly drained soils that are characterized by very high clay content and restrictive layer at a shallow depth, such as 2 meters. And together, that combination kind of makes this kind of a condition visible in the landscape. Waterlogging is very prominent whenever it rains. And when you have waterlogging in a sticky soil, it creates poor trafficable conditions. So ag mechanization or a lot of the operations that require tractors and equipment, we can't really do any of that unless we get rid of this excess water that stays in the landscape. And what happens is then in that case, we usually utilize a surface drainage system that is a way to get rid of excess water from the surface itself by simply reshaping your fields and using a combination of shallow ditches or shallow channels. Or we put a artificial network of perforated plastic pipes underground about 1 meter depth or 90 centimeter depth. That then collects the water, excess water from the soil profile, and routes that through a main pipe into existing drainage channels. I always call agricultural drainage to be the lifeline of crop production here in the Midwest. We pretty much cannot sustain crop production if we did not have artificial drainage here in the Midwest. And this started almost 150 years ago and has continued. Back in the day, they used to put drainage using these clay tiles that were laid in trenches by hand. But nowadays, modern installation is very unique. It's much faster than this, but it uses what they call a corrugated plastic tubing that is perforated. And I have a picture here just to show you. I don't know how much people know about this. So, but typically a large machine, this machine costs about $1 million. And then it can carry up to 3,000, 4,000 feet of a roll of a pipe that is perforated. And then that pipe is installed with a what we call a plow. This plow tip is basically cutting through the soil. It goes underground and it can form, it can go about 6 to 8 feet, so 2 to 3 meters deep into the profile. And then the pipe is coming out of this boot and being laid underground at a depth of 3 to 4 feet or close to 1 meter. This is, as I said, it's a very precise operation that you have to do. So we utilize RTK GPS technology or laser grade technology to maintain grade on the pipes. That's about the US. I wanted to give at least one reference slide for you. I was in India 2-3 years ago, visited Sangli district of Maharashtra. That's where I spent about 15 years of my life during school years. And back in the day, we had feared that over irrigation in this area for sugarcane production might cause some issues. And sure enough, those issues have surfaced in the last decade or so. So waterlogging is a problem. Along with that waterlogging, there is a salinity problem in Western India. And you will see many regions in India that are facing similar problems. But they are trying out drainage in that area now, and we're seeing some of the benefits even in Western India. So what I'm hopeful for is drainage is kind of becoming a technology or aspirational technology here in India as well, and I'm hoping to form some of those collaborations around that. But speaking of modeling of drainage, I wanted to show you a visual of how water actually moves. And some of you who work on groundwater theory, this is not news to you. You're very much aware of equipotential lines and flow lines forming. In case of drainage, the what you're looking at is a drain pipe that is at a shallow depth under soil surface. And this is a sandbox, but dye tracers are showing the flow lines. And a lot of times people don't cannot imagine how drainage actually works in a soil profile. So I thought I'll include this illustration so that kind of brings us back to that drainage theory that was developed based on these principles of how water actually moves through the soil. So, of course, on the theory, I'm not going to spend too much time, but there are basically two classic equations that we always use when it comes to drainage theory. One represents a condition when there is standing water in the field and you have subsurface drains underground, which means you have unrestricted entry of water through a vertical profile right above the plastic pipes. And then we have what we call a steady state equilibrium state when the water table has actually gone below the surface and is now receding at a steady state rate towards down towards the subsurface drain. So Hoogout equation and Kirkham equation are the ones that we use. A lot of times we end up in a situation where the predicted discharge coming into those drain pipes is actually much greater than what the carrying capacity of the pipes is, and we define that as a drainage coefficient. So a lot of times we have to basically assume that the pipe is flowing full, and hence the predicted Q is not really what is coming out of those pipes. Now, when it comes to the reason to even worry about modeling drainage is this fact that there are some side effects when it comes to drainage. A lot of times this drainage network acts as a short circuit pathway where a lot of the nutrients from the root zone can easily leach out through the laterals into the main pipe and essentially find a way into natural waterways, the downstream waterways. And that most of you are probably aware of all the water quality issues across the world. But Lake Erie is what we have on our border. Gulf of Mexico, you probably are aware, that is just south of the United States. We do have these nutrient transport pathways through the river systems that eventually result into eutrophication of these waterways because a lot of the nutrients are coming from source areas. Now, agriculture is one of the source areas. Some of the other examples could be wastewater treatment plants, industry, forests, you name it. Anything that is coming from the landscape that carries nitrogen and phosphorus with it is a contributor. The challenge is what happens when you have a heavily agricultural watershed leading into these water bodies. Then you have large quantities of nitrogen and phosphorus coming from agricultural landscapes causing these problems. So I'm going to kind of quickly go through these slides because I'm not sure how detailed I should be on the background for Great Lakes. Brahma, do you think people would appreciate having a little more detailed orientation on the Great Lakes region?
I think they would know. I mean, what Great
Okay.
Lakes are, but a little bit. I think short introduction would be fine. Should be nice
Okay.
actually.
Okay. So as I said, the water quality issues that we're dealing with are two. One is in the saltwater body. So this Gulf hypoxia is essentially a saltwater body, nitrogen being the limiting factor. Great Lakes region, it's a very large water body. About 20% of the world's fresh water actually lies in this combination of the group of Great Lakes. Large drainage area, 30 to 40 million people depend on it. Huge economic implications. So quality of water in these lakes is very, very important from a recreational use perspective as well as the drinking water use perspective. If you look at Lake Erie, this is Lake Erie, right north of Ohio. This is where the city of Toledo is. That depends on the water from Lake Erie. Lake Erie is kind of unique because it's one of the shallowest Great Lakes, and it kind of poses unique problems. So the state of Ohio is divided about third drains into Lake Erie, and the two-third drains into the Mississippi River watershed through this Ohio River that runs along the south of the state border. And especially this western part of Lake Erie is very shallow. And what happens is whenever you have phosphorus in that water, the shallow depths and the water temperatures, it's a unique combination that fuels algal blooms. And this is kind of a chronology of all the algal blooms we have had since 2002 going all the way up to 2025. As you can see, the severity of algal blooms ranges from one year to another. If you look at this 2008, that kind of became our reference year for setting some of the reduction targets. But the wake-up call was 2014 when the city of Toledo had about 500,000 people that were given do not drink warnings for water because there were cyanotoxins in the water. So that kind of drives some of the emphasis that we have on improving water quality. The interesting thing is what happens is we are in a watershed that is heavily agricultural watershed. So a lot of the focus is on trying to mitigate water quality by doing something in these ag landscapes. I'm keeping Asmita's name here because we, as I said, we do a lot of the collaborative work, a lot of the modeling work at watershed scales. Asmita is the lead, and then I'm part of the team. So I wanted to make sure I acknowledge that here. It's a huge team that is involved. So we're now focusing on a very small part of those Great Lakes, which is the western part of Lake Erie. And we have a watershed that drains into Lake Erie. We call it a Maumee River watershed. Carries about more than 50% of the phosphorus load into Lake Erie. The unique characteristic, anything you see green on this map is agricultural landscape. So you can see how prominent agriculture is in this watershed. 76% of the area is cultivated crops. And the unique thing about this landscape is about 90% of those crops are actually grown on very poorly drained soils that I mentioned. So because of that, we know that there is a presence of artificial drainage in these landscapes. And as soon as you introduce drainage to a soil, the hydrologic pathways change significantly. Instead of having a lot of surface runoff, you then start having a lot of subsurface discharge. And that changes how the nutrients are going to move with it and so on. As I mentioned, we have a large collaborative team. Dr. Margaret Kelsey is kind of the main lead on this whole SWOT modeling project that I'm going to present. But essentially what we do is we use a SWOT model to represent this watershed. But the way we use SWOT model is kind of unique. For those of you who know at least something about SWOT model, it's a watershed scale model that you can set up in a GIS environment. And then the watershed gets divided into sub-watersheds, and the sub-watersheds get divided into what we call hydrologic response units. Typically, a hydrologic response unit in a watershed scale SWOT model would be more like 400, 500 hectares or so. In our case, we developed a very high resolution SWOT model that represents an individual agricultural field. So thousands and thousands of HRUs, and that is the unique nature of this SWOT model. So you can imagine when you try to develop a high resolution SWOT model that can imitate each individual agricultural field, you also need to inform that model with data at those scales. And that's kind of a unique challenge that we took up by essentially using a lot of geospatial data to inform. I'm not going to go too much into details of that. This paper kind of lays out the process for how we have parameterized this model. But many different data sources go into informing that model. We use a lot of remote sensing data. We use within state data for defining concentration of nutrients, especially phosphorus in the soils. We use multiple data sources to define where in the watershed manure might be being applied to soils or being produced. We used sales data from county levels to inform how much fertilizer is being applied in which landscape, and so on. What we're going to focus on is subsurface drainage. Of course, the calibration validation process for a model, a lot of times you might just do that at the outlet of the watershed, but we have uh, enough data across the watershed that we can use gauge data within the watershed to be able to calibrate at sub-watershed scales. Going forward, we also have field scale monitoring through a USDA ARS unit that we have here, as well as some of my monitoring. So just wanted to show you some visuals of how we do our monitoring using automated samplers and automated flow measurements. Um, but all of this data helps us calibrate and validate some of our modeling efforts. So the first thing that played a role in refining our model was typically drainage related parameters are assumed in a SWOT model. And we took a kind of a slightly different approach where we said, why don't we take us extra effort to decide what those drainage parameters might be. So I teach drainage design here in Ohio. And essentially what we did was we took the recommendations from that drainage guide that we utilize based on soil type, parent material, landscape features. And then we use that to guide what drainage parameters, especially drain spacing, you would use for each of those fields or HRUs that we talked about. So in the original model that was published, we had only two drain spacings that they had assumed, which was about 5 meters and 10 meters, 15 feet and 35 feet. And when I started talking to this group, this was very early. I was not involved with this work. And I said, this is not a good assumption. This is 15 feet is too narrow. We do not have that narrow spacing. We need to change this. So then we essentially improved that model to have a good distribution of drain spacings in the watershed across different HRUs. So we took all the HRUs that we had for these two spacings and then changed their drain spacings to be these 30, 35, 40, 50, and 60. And you can see the numbers here in terms of square kilometers that were distributed. All right. So we said, well, the gray dots on this, this is observed discharge at the watershed outlet versus simulated. Our baseline model already had good model efficiency for monthly discharge prediction. By changing the drainage parameters, which is the red dots for calibration or green dots for validation, essentially it didn't do much to improving the discharge predictions at watershed scale. And you might think, well, what's the point of then going the route of having to change all the drain spacings if it's not really affecting your model performance? What happened is it actually affected how our simulations were happening for nitrate leaching, total nitrogen, dissolved phosphorus, and total phosphorus predictions. Model performance actually improved beyond the baseline model once we simply corrected what the drain spacing needs to be in each of those landscapes, which was a really encouraging sign that SWOT model actually was performing better when you started representing the actual drain spacings in those landscapes. So there is a lot more to that study, but I wanted to just show you some of these conclusions that um, the main conclusion is that if you actually represent that intensity of drainage in the landscape, then the model actually becomes much more responsive to your nutrient loss predictions. I'm gonna check where I am at on the time. Okay, I'm hoping to wrap up in another 10 minutes or so.
That's perfectly fine. Perfectly fine.
So this is only one of the parameters that we essentially improved in the model. As I said, we are constantly trying to improve the SWOT model, especially the inputs and the parameters that we use for running the SWOT model. And just wanted to give you a visual representation of how we have done that for factors that are other than drainage. I mentioned the manure application. So animal livestock population is an important component of agroecosystems, and every blue dot that you see here is a dot that has received somewhere between 3 to 193 kilograms per hectare of phosphorus from manure application. So you can see these dots. What you don't see is these are based on what we say call as CAFO locations, concentration animal feeding operations. There is a data set that is behind this that is essentially informing where those locations are for concentrated animal populations, such as 5,000 dairy cows. And then there was a algorithm that we developed for being able to distribute the amount of manure coming out of that kind of a facility within a certain radius. Use of inorganic fertilizer. That is informed by existing soil phosphorus concentration. And this goes directly to soil fertility recommendations. Typically, an agronomist would say, if you have a certain concentration of soil phosphorus, then you should apply this much phosphorus versus that much phosphorus fertilizer. So our recommendation is, if you have soil phosphorus above 50 ppm, do not apply phosphorus fertilizer. So you can see how we are trying to tailor even the agronomic management within each of those fields by that site-specific information. We also are simulating whether you place the fertilizer on top of the surface of the soil or below the surface of the soil in that cultivated land. Wetlands are a big part of this entire landscape, and we wanted to make sure we are able to represent wetlands in the landscape. So those are built into SWOT model. Subsurface drainage we just talked about in detail. And then there are some other practices, essentially conservation practices that you could map using remote sensing data and put into SWOT model. So that's kind of a parameterization of the model. More importantly, you're probably wondering, why are we going in this much detail, and why are we why is this pursuit for perfection with SWOT model? And all of this is driven by the need that we have on the policy and decision side. The state of Ohio has made huge investment, up to $200 million in last 3 years, towards solving water quality problems. And the biggest challenge they have is where do we invest such a large amount of money? So what we do is we actually invite, we have put together a stakeholder group that is made up of many different entities and stakeholders across the state, which include state agencies, federal agencies, some of the commodity organizations, farmer organizations. And this group collectively actually tells us whether or not we are on the right path with respect to representing what is happening in the watershed. So just to give you an example, we might say, hey, this is a practice that might provide water quality benefit. How many farmers do you think would adopt this practice across this watershed? And then this group actually tells us more realistic, in a more realistic way, whether or not that practice is going to be adopted. So here is an example of a practice where you have a conventional drainage system, all the laterals bringing water into a main pipe, and then that main pipe, instead of letting that water discharge into a natural waterway, you put a control structure at it and set a set point so that you can retain water behind that structure and not let it freely flow into a receiving channel. By retaining more water in the field, you're retaining more nutrients in the fields, especially nitrogen and phosphorus. And that essentially becomes a conservation practice that provides the water quality benefit. So we work with our stakeholder advisory group to give them a list of practices, and they give us more realistic scenarios for what percent of landscape would adopt these. Sometimes we also take help from surveys, farmer adoption surveys, our willingness to adopt surveys, and that gives us information on what percent of cultivated land can actually adopt practices like cover crops, no tillage, or water management, or buffers, wetlands, and so on. Then we take one practice at a time, and then we apply it in the landscape, and we see how sensitive um, the outcome would be. So for example, if I wanted to do that control drainage practice, the video that you showed, what is the potential for that practice to reduce phosphorus loss from the entire watershed? The green shading that you see is numbers reported in the literature, and the bars that you see here are numbers that actually SWOT model predicted. So in our case, we saw SWOT model did not predict any benefit of controlled drainage, while the literature says there is a up to 50% reduction with controlled drainage for phosphorus. However, in some cases, we do agree with the literature. For example, putting fertilizer under the soil surface has a significant impact on reducing phosphorus loss up to 50%, and the model actually showed that. So there are some agreements, there are some disagreements. What we do is we then use a combination of these practices and apply that in each individual field. And we call it bundling of these practices. So if you look at these darker, you probably don't see them much, but there are some darker colors. The darkest color means that one field actually received up to 5 conservation practices, a single field, like a stacked conservation practices. When you stack those practices, you actually see a much better improvement in water quality. You see a much better reduction in phosphorus loss from those fields, which is what we have proven here by showing that a bundle of practices gives you much better reduction than having to rely on a single or one or two practices working together. I hope this makes sense. I'm going a little faster because I'm probably over time, but really the benefit of us trying to use these modeling approaches is to then go back to our stakeholders and tell them that, hey, you should not be randomly placing these practices. You should be more strategic in where to implement these practices, and more targeted adoption might actually get you better impact. And then combining practices can actually also get you better impact. So this directly helps educate our policymakers that then can incentivize these packages for farmers that can then adopt these practices and hopefully move us towards water, achieving those water quality goals. And this is my last slide. Uh, I talked about how good the SWOT model is. I didn't talk about how bad it is if you don't know what you're doing in terms of the processes that you're trying to represent. We have three different efforts going on where we are essentially going down to the source code and modifying that source code because we have found that the source code that is built into SWOT and the processes that we use in the SWOT are not adequate when it comes to subsurface drainage representation and nutrient loss. Hydrology wise, we are seeing much better response in SWOT for subsurface drainage representation. But when it comes to phosphorus or nitrogen dynamics, we do see some limitations, and I'm happy to talk about those if we have more time towards the during the conversation. So that's all I have to share. I'm going to stop sharing so that I can see you all.
Yeah.
And hopefully I left some time for question and answers.
Yes, yes, there is definitely. Will not hold you long because already it's past midnight and all. So if there are questions from the audience, I invite them to unmute themselves and ask, or you can also write in the chat as you like. It was a very interesting talk. I mean, I never thought about. To be honest, I did not even know that there's an underground drainage system that exists, right? I mean, and you can actually put artificially also. You can lay pipes and the implication of it. I mean, it's really really interesting. So from this audience, online audience, if there is any question, any clarification, any comment, this is a chance. Or maybe I'll go ahead. You can also raise your hand and then ask. So Vinayak, I wanted to ask a few things actually. So okay, I understand that maybe it's very important for nutrient balance or to understand how but this but isn't it the influx of nutrients also is important, as important as.
Yes,
So where do
absolutely.
you model
Yes.
that in the system, that how much is the influx? And that could be natural or anthropogenic, right? It could be that I don't know. I mean, maybe due to natural systems. Maybe you're adjacent to a forest. It's a different story. If you go deep into human or urban system, then it's a very different story. If you're next to a
Yes.
sewage treatment plant, and where there's a, yeah, so things like that. How can you model that as well?
So that's the advantage of using SWOT model. It does allow you to um, pretty much have major representation for each major land use. So if you do have non-point sources such as forest ecosystems or agro ecosystems, you can parameterize um, the nutrient cycling, including artificial fertilizer application, like external sources of fertilizer application. But if you have wastewater treatment plants that are point sources, you could actually put those into the model that then serve as a point source going into that river.
Mhm.
And then you can assign a concentration and a discharge for those point sources. So
Mhm.
all of this is possible to build within the framework when you're parameterizing the model. The
Mhm.
way we account for nutrient inputs in agroecosystems, it's very easy. It's either a inorganic fertilizer or a organic source like manure or compost, and that's how we do it. But we build, um, in our case, we build 17 different cropping systems, and we applied those. So agriculture is so diverse that this farmer may be doing corn and maize
Yeah.
and soybean rotation with wheat. They might apply maybe 100 kilograms more nitrogen than someone who is not
Yeah.
necessarily doing those three crops. So that is how
Mhm.
we account for those differences.
Nice. And additionally, so you talked about nutrients, and I think in our center we do work a lot on contaminant. So I was wondering about that aspect also. I mean, could you? could you shed your some points or some views on how contaminant can be studied here? And I mean the
Yes,
role that underground drainage system, can play. So I mean I
absolutely.
think draining the soil of nutrients is probably bad, but if you do not drain enough, or you let's say you try to stop it a lot, then you also stopping contaminants, right? Heavy metals and all that come with pesticides and so on.
Yes, yeah. Uh, I have a slide that shows golden rule of drainage. It says drain only what is necessary for trafficability and crop production, not a single drop more. And
Mm.
it's driven by the fact that you will be investing more money into it, but also there are environmental consequences. When it comes to agriculture, the reason we are using nutrient as a term is because it is actually loss of nutrient for the farmer, but it is a contaminant for receiving water bodies downstream, uh,
Oh.
nitrogen or phosphorus. Along with that, yes, there are some researchers that are looking at emerging contaminants, and especially in livestock operations, they are looking at microplastics and
Yes.
PCBs and all of that. I have a research scientist who started looking into 6 ppdq, which comes from tire wear particles into the waters. Doesn't necessarily have huge implications to human health, but fish health is affected by
Yeah.
that. So there are some efforts, but a lot of my effort and time goes into essentially nitrogen and phosphorus and sediment is what we focus on.
Okay.
See a
Okay.
hand raised, and we see a few more questions in the chat.
Yeah, so I think Rajeshi, if you have any question, you may just.
Yeah, I can see many people have already put their questions in the chat box. So I will be quick. Professor Vinayak, this is outstanding presentation, excellent work. I just have quickly two questions. First one is, what is the
I did
soil
not hear that
forcing?
question. I'm sorry. It
Can
was
you
your
hear
No,
me?
voice
no.
was breaking up.
Okay, so
Professor Vinayak,
Rajeshi,
can
your
you
voice
hear
was
me?
breaking, so maybe again.
Am I audible, Brahma?
Yes, yes, you're audible to me. Vinayak,
Yeah.
are you able to hear Rajeshi? No, Rajeshi, can you please write it then maybe? Then I'll ask on your behalf.
Uh,
Okay, in the meantime, we'll go with, I think, with Janki. What parameters do you measure for subsurface?
um, I'll do a screen share quickly because I think you're talking about this slide. So this is actually the unique thing about our research is it's on-farm research. So we don't, I have some plots, but I usually partner with farmers. So you can see how big this field is. This is a
Yeah.
70-acre field. And what we do is at the edge of the field, wherever subsurface drainage pipe is coming out from the ground, we put instrumentation of V-notch there. And we also use topographic analysis to figure out where concentrated flow paths will be, and then put a surface flume for monitoring. And then essentially we are monitoring very much the same parameter for surface pathway as well as subsurface pathway. Number one thing, we measure level of water in the V-notch, and we measure discharge at a 5-minute interval. And then we have these are ISCO automated samplers that are connected with a bubbler level logger, basically. And the idea is this is keeping track of the whether or not there is discharge. As long as there is discharge, the automated sampler is taking, it has a robotic arm inside it, and it is taking composite samples. In a base flow scenario, we take one sample every 6 minutes, every 6 hours, one aliquot every 6 hours, and we composite that over 2 days. But when we have high flow events, we actually go to a high frequency sampling, and we took 15-minute aliquots and composite those over 1 hour into these bottles. So every 2 weeks, we go out and collect these bottles and then bring those back in. So then we analyze these bottles for nitrogen, so total nitrogen, nitrate, total phosphorus, dissolved phosphorus, and sometimes for sediment, especially if it is a surface runoff. We also have a weather station on site that we monitor weather data as well. And then once every 2 years, we go out in this field and take soil samples. That may be useful as well. I hope I answered that question.
Yeah, you did. Now, next was which version of SWAT is used in the study and modified, SWAT 2012 or SWAT Plus?
Yeah, as you can see, this paper was from 2021, so SWAT Plus was very new back then. A lot of our model development has been in SWAT 2012. We have modified source code, so we're still using a stable version of SWAT 2012, and we have a couple of postdocs that are working on translating or transferring all of that to SWAT Plus.
Okay.
We still find SWAT 2012 to be more reliable
Oh,
and
wow.
stable.
I think somebody has asked for sharing article link or DOI. So, I
Absolutely.
mean,
I'll be happy to
yeah,
do that.
yeah, few. And then I think then Prajakta has asked, so the model you demonstrated was calibrated using discharge data. Could you please clarify whether this discharge corresponds to the watershed outlet or a specific drain outlet? I think we know now, but yeah, please go ahead.
Yes, we do calibration only at the watershed and sub-watershed scale. The Apostle et al. 2021 paper is actually based on that approach, but she did eventually compare the data that we have collected at field scales with HRU scale output. We did not necessarily use that to calibrate at HRU scales because we had 8,000, I think 14,000 HRUs to worry about. So it's not practically, it is not possible, but we gain insight from our HRU scale comparison and then utilize it to simply modify some of the parameters during the calibration phase. Good question.
Okay. Okay. Now I think Rajashi's questions are that which soil data was used?
So here, if you're familiar with NRCS, USDA NRCS, which is the Natural Resources Conservation Service, they have a national database of soils, and it is called SURGO, SSURGO, and we use SURGO database to inform our SWOT model. It's pretty high resolution data set for soils, and it comes with a lot of the soil properties that were actually measured using real samples and not necessarily just estimated values. And I think there is a second question there.
Yes.
I'm not sure if you can explain that question better. I'm not sure what you mean by surrogating the SWOT model for an efficient parameter handling. If you're talking about a external tool like SWOT Cup, the Apostle 2021 paper was all based on a kind of a semi-automated process of calibration outside of SWOT Cup. I'm not sure if that's what you were asking.
Rajesh, hopefully this answers or.
Yeah, am I audible?
There are tools available for automated calibration, and we have not done that. Now we are doing it after we complicated our model and we have too many parameters to deal with. Now we're trying to use some of those programs.
Okay. Moving on, I think what are your suggestions to model nutrient flow in a quite large watershed where data is really scarce and also limited calibration data on nutrients, especially considering Indian conditions? Which default SWOT parameters should be considered for tuning, as there are more than 500 parameters in SWOT?
SWOT, the core developer team for SWOT model still so they still firmly believe that they have developed SWOT for ungauged watersheds. At least that's what they want to suggest. the challenge is that 500 plus parameters that you have to deal with. This is a question I cannot answer. Unfortunately, I do not do hardcore SWOT modeling. I lead some of those efforts, but Asmita is deep into the parameters. In terms of the nutrient cycling for conditions like India, the most important factors would be the amount of fertilizer input that you're seeing in that watershed. That is number one. Getting a correct amount of input that is coming into your watershed for nutrient is probably the biggest factor. As I said, someone got creative. They looked at fertilizer sales data at county levels, and then they came up with saying that, okay, well, the probability distribution matches with the sales data, and that's how we know that this county is applying this much fertilizer. So that is a very important factor, in my opinion. And other than that, I would defer to Asmita. You probably should just reach out to her and she can guide you on that. The other suggestion I have is to simply look at some of the SWOT user groups, and they might give you better insights than what I can. The one thing that we don't worry about here in this landscape is groundwater, transport of nutrients to groundwater, mainly because we have this interceptor system. The drainage systems intercept a lot of the subsurface movement and they discharge it into our surface water. So a lot of times we don't really worry about groundwater. A lot of times our groundwater concentrations are stable. Depending upon which region you're simulating in India, movement of nutrients down to groundwater would probably become an important consideration as well.
Yeah, thank you. I think what Rajesh was asking was machine learning based model surrogates, and he's also put a
Okay.
couple of
Yeah.
his papers where I think they have demonstrated this
Okay.
in the chat.
I will look into that for sure. So this one paper is on downscaling flash flood.
I mean, I was
Yeah.
wondering that maybe
Okay.
we should also invite Ashmita to give a talk, isn't it? For SWOT based questions or SWOT related analysis.
Absolutely. I think, yeah, she would have done this much better than I did, but yes, yeah, definitely. If you want to do a follow-up talk, I think Asmita may be a good speaker to
Perfect.
talk to. I
Any
would be
more
interested in
questions?
talking to you more, Rajeshri, and understanding this better outside of the time that we have right now. There's one more.
Yes,
I
thanks.
thought there was someone had a hand raised.
I think Prajakta says, sir, I'm curious to know in the study area you presented, what are the sources of irrigation? Surface water, groundwater. Also, what irrigation method are being used, such as furrow, flow, or drip?
You'd be surprised to know that there is hardly any irrigation in this landscape. In Ohio, especially, as I said, we get 100 centimeters of rainfall. About 50 comes during non-growing season, but the other 50 comes during growing season, and it's divided pretty much equally. Every month we get about 7 to 10 centimeters of rainfall. So, and they grow only one crop between the month of May and October. So a lot of the landscape here is rain-fed. The only irrigation you will see is for specialty crops like horticultural crops, and that's very tiny amount. Out of that 72% of cropland, maybe 70% is either maize or soybean grain cropping systems that are rain fed, and maybe 2% would be something that is specialty crops.
Oh.
So that's another thing we don't have to worry about in SWOT.
Okay, I think I will not like to hold you longer. It's too late there in the US. Thanks a lot for doing this. And uh, I think we all learned a lot today. Very interesting aspects. And I think something similar should be done for India also. We might be struggling with data, but I think there are novel or there are interesting, innovative ways through which we can apply this and make things work out,
Yeah.
or knowledge can be generated here for Indian scenarios.
Yeah.
Thank you again for doing this talk. So I think his email address is available for anyone to contact him. You can write questions, you can have any request you have with Professor Vinayak, you can directly reach out to him. I will also do the same. We shall connect once more, I think, just to see uh, what interesting aspects, we could work
Yeah.
together. And with this, again, I'll close the seminar. And thank you, Professor, for
Thank you.
joining and for giving this very insightful and exciting talk. Thank you very much. Thank you all.
Thank you for the invitation, and it was very nice talking to you all. And one thing I would mention is that I am very much interested in the work that you have done recently on the groundwater that Maya presented. We are seeing a opposite end of this is water availability for other sectors, and there are only a small section of our state that is facing that issue now, and there is some need now for us to actually look into groundwater modeling. So I'm hoping that
Yes.
I can connect with you and your group at some point and learn a little more. So,
Yes,
but
yes, yes.
thank you again.
100% will do that. Thank you so much. Thank you. Next time you are here in India, just let us know. We'll invite you over to ISC for a personal visit also. We would love to have you.
I'll be happy to. Yeah, that would be
And
great.
the invitation is for your wife as well, Ashmita also. She can also come. I mean,
I
whosoever,
will let her
whenever.
know.
Yeah, okay. Yeah,
Yeah.
thank you
All
so
right.
much. Thank you.
Thank you. Have
Take
a
care.
nice
Bye
day.
bye. Bye
Bye
bye.
bye.
You too. Bye.